Thank you for coming. I'm Jiannan from Washington State University. Today, I'm going to give a talk about my most recent work, cuSZ, high-performance GPU-based lossy compression framework for scientific data. Let me first give background, the trend of supercomputing systems. The compute capability is ever growing, and if we look into the peak performance. But if we look into the right-hand side, the peak performance versus the storage bandwidth, we find that the gap between the compute and I/O is a large year by year. And this causes problem. This is limiting the scalability of the scientific application. If we look into the current status of the applications, it's about big data. It's generating large amount of data, and it's increasing the hardware budget for storage. Another example could be APSU brain initiatives. The experiments are done on one side of the Argonne National Lab campus, but the data processing is on the other side over the limited bandwidth because of big data. So passively, the large amount of data can use up the file system, and it takes too long to store. And the data processing could not be on time because of the limited bandwidth. The solution could be data reduction. And we need a data reduction rate at 10 and sometimes 100. So if we look into the lossless compression, it's not really effective because of the randomness from the floating point data representation. It's non-repeated and non-patterned. If we put side by side, we find that floating point represented data could be really random, just like noise. And we look into the lossy compression. We got inspiration from industry lossy compressor because it provides much higher reduction rate, hundreds of thousands. The problem being, it's not designed for scientific data, and it lacks strict error control, which is widely important for scientific discovery and accurate post-analysis. In addition, we need diverse compression modes, absolute, pointwise relative, L2 norm, and fixed rate. SC is a strictly error controllable lossy compressor designed for scientific data and is prediction based. The framework of SC could be put this way. It first takes the prediction error into the quantization and translating the floating point to integers, which is much easier to compress using entropy encoders. And a good predictor can be really helpful for achieving low entropy. So motivation, we want to bring error controlled IC to GPU, and we want to bring high throughput to IC because the current CPU version can only achieve relatively low throughput. So cuSZ is high performance error bounded lossy compressor on GPU for scientific data based on IC. And we have challenges, of course. The first one is the type dependency, low carried rate after write dependency, which hinders parallelization of any form, either pipelining or CMD/CMT. So what do? The solution is that we eliminate the dependency and parallelize it. And the next challenge could be task scheduling. When we speak GPU, we think of the heterogeneous computing. It's about assigning tasks to the CPU and GPU based on the task feature. But in our case, if we really do this, assigning the GPU and CPU to do the job, and based on what they are good at, we can see high overhead from the host device synchronization and communication. So what do we do? All tasks are done on GPU. To wrap up, our contribution could be we use a dequantization technique to parallelize to eliminate and parallelize it. And we carefully modularize and parallelize the Huffman subprocedures. And again, cuSZ is the first strictly error-bounded lossy compressor on GPU for scientific data. And this is a workflow: pre-quantization, prediction, post-quantization. And we put the quantization code into Huffman encoding, histogramming, getting canonized the Huffman codebook, and do the encoding by memory copy, basically. And now we're looking into the loop-carried reductive rate dependency in SD. SD makes it to be decompressed or reconstructed data show up during the compression and make it under our control. The decompression is basically replay this part. The error control is over the prediction error and is done during the quantization and reconstruction. And this introduces loop carried reductive rate dependency, which is marked with error in the right-hand figure. So to parallelize it, we prioritize the error control. We do the error control over the original data. And after that, we just set a barrier right after the pre-quantization. And we change the data dependency, still marked by that arrow. And look side by side, we can fully parallelize it. Next, it's about Huffman encoding. We use canonized codebook because it's transformed into a compact manner. And during the decoding, we don't need a tree. The current tree building is on GPU. It takes 4 to 7 milliseconds. It's to be optimized. And the canonizing codebook is shorter, taking up only 200 microsecond for 1,000 symbols. Encoding and decoding is done in cross-grained manner, and the optimizing is tuning the degree of parallelism. So the whole application is a mixture of different parallelisms, and it includes a sequential, cross-grained, and fine-grained parallelization, and hardware-supported atomic rate. It's worth noting that in canonizing codebook, we can see the problem size exceeding the maximum allowed thread block size, which is 1,000. And we utilize the zero-out cooperative group API to achieve the synchronize across the whole grid. So, tuning the cross-grained Huffman codec. On V100, we found that if we set the thread number at around 20,000, we can achieve the optimum throughput. So the evaluation is set up this way. It's on NVIDIA V100, and the comparison baseline is IC 1.4 and the cuZFB. And we use real-world datasets from HPC domain. So the performance. If we look into the third column, prediction and quantization, with fully parallelized dequantization, we can achieve over 200 gigabit a second. And Huffman coding is not including the tree building time. And we achieve relatively lower But in the end, the compression kernel can still achieve over 40 gigabits per second. The communication over PCIe is an equivalent value because of the compression ratio. And overall, we can still achieve over 20 gigabits per second, which is comparable to cuSZ. And we also compare the performance to single core and multi-core CPU. To single core is over over 200 times, and comparing to OMP, you can still achieve over 10 times the throughput. And another aspect to evaluate is about compression quality. We choose relatively high compression Rate-Distortion at 85 decibel, and we show Hurricane and Nix here. So in general, we can achieve higher data quality with the same bit rate if we look into this figure. And future work includes keep optimizing and thinking of the scenarios of in-memory compression on GPU. So this project is supported by Exascale computing project and NSF. And thank you.